Hello. In this video, we're going to talk about infinite limits and vertical asymptotes on the graph of a function. By infinite limit, I mean a situation where a function is blowing up to positive infinity or blowing down to negative infinity, something where the curve is shooting rapidly upwards or downwards along an asymptote. And we're going to phrase all of these things in terms of limits and apply them to a few examples in this video. I'm going to start with the example of the function f of x equals 1 over x. That's the curve you see graphed in red on the right over here. It has those two pieces. And I have some points marked on the curve that we're going to talk about in a second to try to convince you that these two limits are true. And I think you can kind of see what they say and how you could infer that information from the graph. This first one is saying that as I approach 0 from the right, if I plug in very small positive numbers for x, so in other words, like over here, then the corresponding outputs, the y values of the function, are going to get bigger and bigger and not be bounded by some upper limit. They're just going to continue to grow and grow up to positive infinity, and that's what that statement really says. Meanwhile, on the other side, as I approach 0 from the left, if I plug in very small negative numbers, the values become very, very large and negatives, and that's what that says. So I think both of these are based upon an idea that we're going to use a lot, which is essentially if I divide by a very tiny number, that causes the result to be a very huge number, essentially. So let's talk about that first limit as I approach 0 from the right. Then if I make x 1, then the corresponding output is 1 over 1, it's positive 1. Whereas if I make x something a little bit smaller, like 0.1 or 1/10, f of 0.1 is 1 over 0.1, or it's 1 divided by a tenth, or it outputs a positive 10. And that's that purple dot you see up there on the graph. That's the input 1/10, very small, close to 0. The output is relatively large, up there at 10. And if I make x something even tinier, but still positive, so closer to 0, but still on the right side, f of 0.01, or f of 1 out of 100, is going to be 100, and that's going to be, well, it's way up there above the screen, you can't see it, but there's a purple dot way up there, very close to the y-axis and very high up. And likewise, if I have x equals let's just make something a lot smaller, like that, that's one part in 1, 2, 3, 4, 10 to the 4 is 10,000. Well, f of that number is 1 over 1/10,000th, so it's going to output 10,000. If I keep going and make those numbers get closer to 0, these numbers are just going to keep growing and growing and growing, and that's exactly what this limit says in that limit notation that we've been developing, and that's exactly what I see here on the curve, and that's exactly why we call this a vertical asymptote. It doesn't actually matter that this is also happening over here. The mere fact of this piece of the curve shooting upwards like that means that this graph deserves to have a vertical asymptote there. And so the idea that's kind of showing up over and over in those calculations is that if I do 1 divided by a super tiny but positive number, that outputs a huge positive number. And I know that's a very cartoonish way of saying that, but that's really the principle that's happening here. And this is kind of what I envision in my head when I think about something like this. I think of a tiny number in the bottom of a fraction, the reciprocal of a tiny number, as being a really huge, gigantic number. And so what about the limit approaching 0 from the left on the other side of the graph? Well, that's really no different if I have 1 divided by a really tiny negative number. That doesn't change the fact that it's going to be huge in magnitude and absolute value. It's just going to make it a negative number instead, and that's exactly why I see this happening going that way, and this is why we would include this vertical asymptote at the x-axis, or sorry, the y-axis there. And so really the definition of vertical asymptote, something that I assume you've talked about before in an algebra or pre-calculus course, really the definition of a vertical asymptote is if a limit like this is positive infinity or negative infinity, that's what causes the presence of a vertical asymptote like that. Let's look at a similar function, but with a slightly different scenario, which is the function 1 over x squared instead. How is that going to change things? Well, let's try to employ a similar analysis here. If I plug in x equals 1, I get the corresponding height of 1 over 1 squared, or just 1. That's that point over there on the graph that you see. If I plug in 1/10 or 0.1, then the function will output 1 over that number squared. And so in other words, 1 over 10 squared is 1 over 100, and then 1 divided by that, the reciprocal of that reciprocal is 10 squared, it's 100. And so just like in the previous example where I plugged in 1/10 and I got 10 as an output, very tall, I have an even more striking phenomenon here where when I plug in 1/10, the height is not 10, but way up there, the squared of that height of 100. And that's very tall. And if I take something even tinier like 0.01, f of 100th or 0.01, I would get 1 over 100th all squared, so that I have a reciprocal of a reciprocal situation. So the output is going to be 100 squared, or 10 to the 4th, or 10,000. And so as I keep moving x closer to 0 and make it really tiny, I have 1 over something squared, and that's going to make the number huge, and even kind of huger than the previous example. The square is making that happen. So if x is a really tiny positive number, then what I have is f of x is 1 over a tiny positive all squared, and that's going to make an even tinier positive number in the bottom. And so it's going to output a huger positive number. I know this is very vague and informal, but this is kind of what's happening, and this is really what I think about in my head. If x is a tiny number, squaring it makes it even tinier, very small. Like the 1 out of 100, that's a small number, but when I square that, I get 1 out of 10,000, and that's a super tiny number. And so I can see this curve not just shooting upwards along the y-axis being a vertical asymptote, but I hope that you can even see the square is causing it to be a steeper, more pronounced growth than the previous example we were just looking at, just the 1 over x. But also the big difference between this and the previous example is that even as I approach 0 from the left, if I have a negative input, then the same stuff is going to happen, and the squaring is going to make it so that I still have positive outputs happening. As I approach 0 from the left and have a negative input, what is that going to change? If I had a tiny negative instead, f of x would be 1 over that tiny negative all squared, and that would make it a tinier number in value, and the fact that it's squared is going to make it so that I do end up with a positive. Even when I plugged in a negative input, I'm still going to end up with a positive output, and that's why I see this curve approaching positive infinity up that way. And so even in this example, I would still say that the limit as x approaches 0 of this function does not exist because it's not approaching a specific number. And so in this case, it doesn't really matter that it's positive infinity on both sides, as opposed to the previous example where it's positive infinity one way and negative infinity the other. I would still say that this limit does not exist because it's not approaching a specific number. Here's another example of a function that's not a rational function, a ratio of polynomials like that. Let's look at the natural log graph, this logarithmic curve. It has a vertical asymptote at x equals 0 as well, and this situation is a little bit different than the previous one. So if x is a tiny positive number, imagine I'm plugging in something very close to 0 but just to the right. That's what I mean here. Or in other words, if I'm taking x values that are approaching 0 along the x-axis like that, then the corresponding outputs are going to become larger and larger and larger negative numbers. Why is that happening? Well, the main idea is that the logarithmic curve, ln, natural log, it's the inverse of the exponential growth curve, e to the x. So down here I have the logarithmic curve graphed again, and in case you are unsure of where that's coming from, as long as you know what the exponential curve looks like, then its mirror image across this diagonal line y equals x, that's the logarithmic curve. Because they're inverses, it's like swapping their x and y coordinates. So like this point here is at a certain x and y value. If I swap them, I get the corresponding point over here. It's its mirror image across the line y equals x. And that's what I have stated here as well. So I think sometimes it might be easier to think about exponential things like this and then translate into logarithmic things. So if x is a really tiny positive number, how can I make e to the y? How can I make y some number that will make it output that really tiny positive? Well, the thing is I have to make y a really big negative. So like, for example, if I make y -2, I know that's not a very big negative, but it's a negative number, that's going to cause the output e to the y to be a small positive number, because a negative exponent is like division, 1 divided by e squared, and that's about 0.13 or so. That's a relatively tiny number. And meanwhile, if I make y a slightly bigger negative, like -10, that's 1 divided by e to the 10th. Now, e to the 10th is like a really big number, so 1 divided by that is this really tiny number with 0.0000 something, and that's a really tiny number. So another way of saying those two things in the inverse, in the logarithmic language, is that log of a tiny number gives me a pretty big negative number, and log of an even tinier positive number gives me an even bigger negative number. And that's exactly what these points on the curve are showing me down here. The other thing you may notice is that I was only able to ask about the limit as x approaches 0 from the right. There's no such thing as a 0 from the left part here because of the domain of this function. And so because of that, the asking for the limit of this function as x approaches 0 from the left has no meaning. It's almost like it doesn't even have a chance to exist because there's no function defined over there. It's outside of the domain. Okay, for the next couple of slides, I'm going to use this one function up here, this rational function f of x, this ratio of polynomials. In this case, I have a quadratic divided by another one. I'm going to use this same function to ask and answer a few different questions. And here's the graph of the function from Desmos down there, just to have something to look at, but everything we're going to do, we should be able to do without necessarily having a good picture like that. The first question I might ask is, what happens as x approaches -2? And one thing that we've been learning in previous notes and videos and examples is that, at least for a rational function like this, a first approach is to just plug into the function and see what happens. Because if you get an output, in other words, the function exists there, we have talked about how the rational functions and polynomials are nice enough so that if the function exists, that is what the limit is supposed to be. And so there I'm evaluating that limit by just plugging in -2 into the function. In this case I get 0 over 12. And my main point for this is that that does exist. 0 divided by something, as long as it's not 0 in the bottom, 0 divided by a non-zero number, that is 0, and that is what the limit is supposed to be. I don't have division by 0. I have division of 0, and that's fine. And that's exactly what this x-intercept of the curve is there, -2, 0. That's what we just discovered in that example there. Now how about something like as x approaches 0? Well, maybe I'll try the same approach. Unfortunately, that plug-and-chug approach doesn't work here for this rational function because at x equals 0, this function would be asking me to do 0 divided by 0, and that division by 0, that's a problem. That's something that's undefined. This doesn't have a meaning. So what that means is, well, two things. First of all, there's a hole in the graph there. I know I've marked a point there in red just to make sure that you can see what Desmos wouldn't normally show you, which is that that's a hole. Usually you wouldn't be able to see that. It would just be an unbroken purple curve there. So I'm marking that dot in red to say that there's a hole there, and that the function really isn't defined at x equals 0. And yet we can see from the graph that it seems to be approaching a very particular y value, a y coordinate, a certain height, right at that place. So how can I discover what that is? And by the way, it turns out that it's -1/2. How do I do that? Well, it turns out what we're going to do is factor and simplify this function. This function f of x, if I factor the top into x times x plus 2, so pulling out a factor of x, and in the bottom also pulling out a factor of x, x times x minus 4, it looks like I can kind of cancel those two things, the x factors in the top and the bottom. And so I've summarized that down here in the quotes here, which is f of x is, and I was actually very careful here to not write equals, because when I do that canceling of the x's, I'm glossing over the fact that this function here, the way I've originally defined f, has no meaning when x is 0. I can't plug in 0, I got that 0 over 0 undefined problem. And yet this new version, after I factored and simplified by canceling out those common x factors from the top and the bottom, I get an expression that does exist when x is 0. If I plug in x equals 0 into that expression, I get 0 plus 2, or 2, divided by 0 minus 4 or negative 4, and that's really where that negative 1/2 comes from. So here's the thing, if you open up Desmos and you graph this function here, x plus 2 over x minus 4, you will see exactly this same curve that you see in purple here, my graph of the original function f. Their only difference will be whether or not that point at x equals 0 is a whole or a solid point. For this expression, x plus 2 over x minus 4, that's going to be a solid dot. That point exists on the curve. But for the original function f, as I defined it, it deserves to have a hole there at x equals 0 because it doesn't have a meaning at x equals 0. That's the big difference. Factoring and simplifying reveals what that limit is, but I am slightly modifying the function by plugging up or removing a hole. All right, on the next slide we're going to talk about these other two examples, what's happening around this vertical asymptote at x equals 4. On the next slide, that is. You could try evaluating this limit as x approaches 4. Let's just focus on from the right for now. I could try evaluating that by plugging in. I'll save you the trouble. If you plug in 4 for x, you get 16 plus 8, so you get 24 over 0. You get 24 over 0. So thank you for catching that little typo there. I didn't mean to say 0 over 0. I meant a specific number, 24 divided by 0. So now that I've recognized that there's no point on this graph at x equals 4, how can I still start to think about what's happening as x approaches 4 from the right? What is the curve doing? What are the outputs of the function, the y values, doing? Well, let's do the same factoring and canceling that we did earlier. And then I'll see that around x equals 4, if I take that expression, if x is close to 4, the top, x plus 2, is approximately 6. I'm going to use that to mean approximately, or close to. But meanwhile, what's the bottom of the fraction doing? If I have x minus 4, that's going to be approximately 0 if x is really close to 4. And so now is where it matters whether I'm approaching 4 from the right or from the left. If I'm approaching from the right, if x approaches 4 from the right, then x minus 4 itself is going to be, yes, very close to 0, but it's going to be a very tiny positive number. If x is slightly greater than 4, then x minus 4 is just slightly bigger than 0. It's a very tiny positive. And so what I have for my function is something that's pretty close to 6 on the top. It will be a little bit bigger than 6, although that doesn't matter too much to us right now, just that it's around that constant number of 6. And the bottom is going to be a very, very tiny positive number, and based on what we were talking about on the first slide with 1 over x, this is why I started the video with that example, I have something, a fixed number, in this case 6 instead of 1, like the first example, but a fixed number divided by a really, really tiny positive number, and that's going to make it a huge positive number as an output. And that's why I see this section of the curve shooting up like that. As I approach 4 from the right, as I approach that asymptote, the curve is going to shoot upwards like that. Meanwhile, if I were to approach 4 from the left and approach from the other side of the asymptote, the only difference there would be the top is still going to be around 6, but the bottom is going to be a very tiny negative number, because if x is approaching 4 from the left, from below, then x minus 4 is going to be a really, really tiny number, but slightly negative. It's going to be a little bit smaller than 0. So when I do this ratio over here, I have 6 divided by a tiny negative number instead. It's going to make a huge negative output, and that's what I see happening on the other side of the curve. So yes, we can see this happening on the graph, but I'm hoping this example here can show you how thinking carefully will reveal to you exactly what you see on the graph. It doesn't have to be some black magic where you put something into a calculator and it gives you the graph and there's no reason behind what it's doing. You can predict, you can see, you can intuit why this is happening. And I know it's a little vague to talk about these tiny and huge positive negatives, but I have found it really helpful to think that way, and I hope you find it helpful as well. Okay, that's all for now. See you next time.